Yeah, thank you. Thank you. So, dear friends, good evening. Myself, DK Jha, chemistry faculty and the director of Vision 40. I'm very thankful to Mr. Kiran. He has invited me to just give this lecture on behalf of his KP Academy. I'm very thankful to Mr. Kiran. And what I know about this class, that this is all about how to take advanced level, how to teach advanced level, what to teach advanced level, how to approach. One thing is very clear, that there is no separate advanced level teaching. Without basic understanding of subject, advanced level of teaching is not possible. I know I address this time very learned person, very aspiring and inspiring persons. Most of the faculty members are here. So I do one thing. If I will give some lecture what to teach and what not to teach, that won't be enough. So I do one thing. I take one topic and then I discuss the approach, what genuinely we should take for the advanced level, right? So I hope you know the width of the organic chemistry. It's very wide. There are the two kind of teaching. One is the functional group wise, another one is reactions wise. There is one reaction which is really very important one, and uh, it is not only important, it is very core concept of many of the reactions, or many of the, you can say that other reactions, directly, indirectly, many questions are involved. So I take today uh, the radical substitution, right? I take today radical substitution. Radical substitution. Generally, you will not find much to teach, but honestly speaking, there are lots of things to teach. Okay, there are lots of things to teach. One minute, just I see the chat. Sound is not clear. Is it audible now? Is it okay now? Mr. Shankar, is it audible? Is it better now? Yeah, okay, fine. So I said that we take here one topic, that is the radical substitution, and the best example of the radical substitution is best example is halogenation, photohalogenation of alkenes. Photohalogenation of alkenes. Photohalogenation of alkenes. One thing I request you, that generally what happens here on this Zoom, that sometimes it becomes blurred. But again, again it becomes okay by itself. So you may have some disturbance momentarily, immediately that is rectified. Hmm. So photohalogenation of alkanes, I take here the simple example that here it is RH reacts with the X2 in the presence of H nu sunlight, that gives Rx in there the Hx. This is one of the simple reactions, right? Now the point is, as I told you, it will be clear by itself, right? Now there, that because of some network issue, it becomes blurred again. It okay. RH reacts with X2 in the presence of H nu, that gives Rx in Hx, right? Here H nu is written. What is the purpose of this H nu? Purpose of this H nu, that represents here the sunlight. You know, H nu is the energy of the photon. Sunlight. So you will say that, sir, does it mean that students may ask, sir, does it mean that this reaction is possible in the sunlight, any kind of sunlight? No. As it's matter of energy, so light is made up of so many waves, and all those waves have the different frequency, different wavelength. So all cannot be appropriate for this kind of gigs. What will be the requirement of the energy required here, that only will be appropriate. And that one is basically ultraviolet rays. Ultraviolet rays. And that's why sometimes you'll find directly written UV. Okay. Then next question will be there. What is the need of this energy? This energy is required to initiate the process. Where, from where this starts? X2 is there, homoatomic one, that consumes that energy and gets dissociated into 2x halogen atoms, free radicals, right? One of the students can ask, or there is one question that, sir, does it mean that this reaction is possible only in the sunlight? Sunlight, in this case, is the source of energy, and if there is any other source of energy, not getting voice, really. I hope sometimes momentary problem is happening, but you will be getting. Okay, now. Now you see this one. This time it is very clear. Okay. So, in the absence of sunlight, also this reaction is possible. And that time, here you can say, or in dark, around 350 degrees C of temperature is required to perform this reaction. This is possible. What is the use of energy? Already you have seen that this energy is consumed. Basically, that is used up for the dissociation of this homoatomic molecule into active free radicals. Now, active species formed. And here, that X now will react with RH and X free radical. The halogen atom what forms that induces here this hydrogen to be dissociated homolytically for homolytic cleavage. There are the two types of homolytic cleavage. One is direct on heating, other one is due to induction. Here, one of the halogen induces this one for homolytic cleavage. When one of the radical, this one, approaches that needs one of the atom with one electron, unpaired electron, and so that will induce that kind of dissociation. And that's why here it dissociates and forms R dot in the HX, alkyl free radical forms. What bond dissociates here? The CH bond. R represents alkyl group. There is a C. CH bond dissociation takes place. Alkyl free radical forms in HX. Right? Now what happens here? This alkyl free radical what forms that is surrounded by many of the halogens, right? And now this will induce other halogens for this kind of cleavage, and so we get here the Rx and there the HX, Rx and HX. Okay. Rx and there the HX. Here, there is one question that there is already one of the halogen free radical halogen atom is used up here, so other one is left that may combine with this one. Rx will form. This is not the way a reaction really proceeds. If it happens, sorry, just 1 minute. Just 2 minutes, please. Whatever halogen atom forms this way, the reaction does not take place that way. This reaction has to depend on the continuous source of energy, then only this reaction will be taking place. That will be non-spontaneous. So the main path of reaction is this one, that, or you understand this one, that amount of energy what is required in the beginning, that is just for initiation of the reaction, not for this progress of the reaction. That is just for initiation of the reaction, not for the progress of the reaction. Initiated. Now there the alkyl free radical forms. That alkyl free radical will be surrounded with many of the halogens. Most of the halogens are there in the molecular state only, and that will be combining again their Rx. Sorry. Here, yes, Rx and there the X free radical forms. This X will again come to the new RH alkane. Again, alkyl free radical forms, H6 forms. Alkyl free radical will combine with other X2. In this way, reaction is going on. We say these states chain propagation. Chain propagation. What is chain propagation? Chain propagation when one of the radical being disappeared produce a new free radical. New free radical or new active species. Because if the new active species will form, that will push the reaction forward and the reaction keep on going. Here, one of the free radical X, one of the active species halogen atom disappears, a new free radical R alkyl free radical forms. That gets disappeared in new free radical halogen atom forms. And these steps are getting repeated, and there you are getting HX, you are getting the RX. This is the way RX and HX forms. In this process, if by mistake or there due to some reason, certainly reaction is going on, and with the time there the concentration of this RH in X2 keep on decreasing, then there the nature of the reaction also keep on changing. So there is chance that this alkyl free radical what forms that may combine with the other alkyl free radical if not enough X2 present near and around. Then we'll be giving here the R in R. Other possibilities there that alkyl free radical what is there that may combine with the halogen atom already present there, which is working in some other propagation, and will form here the RX. And one more thing is there, the halogen atom with the halogen atom will form here the X2. But one thing is there, if any of these steps, any of this kind of reaction is taking place, with that one, the propagation, the progress of the reaction is restricted, or there the terminated, the reaction gets terminated. There the progress of the reaction is suppressed. No more there that RX and HX will form. Growth center. Every radical propagation is the growth center. Growth center means their products are yield is coming out. Now this is the point here. That's what these are the termination steps. Actual reaction means chain propagation, and this first step is called initiation, as we discussed earlier. This one is initiation, and this one propagation. Right here. Now this is the general, you can say that background of this one, because this is for the IP also, but this is the basis of all our discussion. Here what we are going to discuss regarding this, that I am telling you, we are going to discuss here the kinetics of this reaction. We are going to discuss here the regio chemistry of this reaction. We are going to discuss here the stereochemistry of this reaction. All right. Our discussion will be there in this way. We will discuss kinetics of this reaction. We will discuss the regiochemistry. We will discuss here the stereochemistry. Right? That will be our discussion. Fine. So let's start with the kinetics. But first, you keep this thing in your mind that chain propagation is the main course of the reaction, because if you will cancel this one there, the R free radical, X2, and there this X free radical, this X free radical, you are getting RH plus X2, that gives RX plus HX. Stoichiometrically also balanced, right? Okay, let's here take this aspect. We discuss here the kinetics. What do you mean by kinetics? This one is certainly the complex reaction. Complex reaction doesn't mean they are the really complex. Complex reaction means all those reactions which proceed in more than one step. And really, we have seen here, they are the more than one step. And whenever we deal such reactions, there we must understand that one of the step, which is the slowest step, that is the rate determining step. Which one is the rate determining step here? And we cannot say that initiation or the termination, because these are not the part of the reaction. Two things are there. CP1 chain propagation first step, and chain propagation second stage. Which one is the earliest? In the kinetics, you understand this one, that very first thing, that CH bond dissociation, right? CH bond dissociation. I mean to say free radical formation. What free radical? There the R free radical, alkyl free radical formation. That one is RDS, ray determining state. With this one, what you interpret? With this one, you interpret that what are those factors which affect the rate of the rays? Okay. So you understand this one. Then we can make one inference here. As the CH bond dissociation, so if the CH bond is reactive, if that has more tendency to be dissociated, this reaction will be faster. So higher the reactivity of CH, faster this reaction. First point. Second point is, there after the dissociation it forms free radical. The free radical is the product of that state. So greater the stability of this free radical, this product, faster the reaction. Sometimes you think that both are same, sir, because if the CH is more reactive, then the product is more stable. The product is more stable, then that will be more reactive. Not always. Sometimes, I just give one example. Okay. Here, first I say the reactivity of CH, it all depends on reactivity of CH. And that's why this neopentyl system there, the CH3, CH2, and there the H. Yes, this one is more reactive than the secondary one. There the CH3, and there the H. If you see this one, then this reacts faster than this one. There is the inductomanic effect. Here this CH is more reactive because of inductomanic effect, right? Inductomanic effect is, you know, the temporary effect. In the reaction condition, it arises, right? And that is along there the CC single bond, right? It is the extension of inductive effect, right? And that's why this one is more reactive in terms of this. Second thing, free radical stability. Why I have mentioned this one? Because this is little exceptional one. You know, if you see here the free radical stability, what I'm writing now, free radical stability is also the driving factor, and that's why here you can say directly, greater the stability of free radical, faster the reaction. Greater the stability of free radical, faster the reaction. In free radical stability, you know, tertiary is more reactive. Tertiary alkyl, that is more reactive. Then there the secondary alkyl, and then there the primary alkyl. Excluding this example, right? There is different phenomena, as I explained you, inductomanic effect. This entire group is putting much inductomanic effect. Because of that, this becomes more reactive, and that's why this is more reactive than this secondary. This is primary, but this is more reactive than the secondary. This thing you keep in your mind. Okay. Free radical stability, in general, you follow this one: tertiary, secondary, and primary. Okay. This is one of the things. Second thing here only you can say, for example, if I take here CH4 plus there the Cl2, that gives here the CH3Cl, and there the HCl. And this is the first reaction, and this one is second reaction. This one is CD4 This one is CD4 plus Cl2 H nu. That gives CD3Cl. There that DCl. Now the point is compare R1 and R2. R1 and R2. Compare R1 and R2. Which one is faster? If you have any confusion or if you are forgetting here something, if you need revision, then I want to revise this point that CD bond is stronger than the CH bond. CD needs more energy to be dissociated into free radical in comparison to CH. That I am telling you. Many of you know. So in this comparison, what you will say? Which one is faster, R1 or R2? Certainly R1, right? Because the CH bond dissociation is RDS. CH bond dissociation is the RDS, and there that CH bond dissociates better, faster than the CD. Okay. If here only, I just write here one question that if this one is third reaction, that is CH4 plus Cl2 37. Cl2 37 isotopic chlorine in the presence of H nu. What you will get here? You will get here the CH3 Cl. This one is 37. This one is certainly 35. You know, plus HCl 37. Now what do you say? What do you say in this case? In this case, I ask here the comparison of R1 and there that R3. What do you say? R1 and R3. R1 and R3. Compare. Again, you will find this one way. This one is the lighter isotope that will be dissociated faster, better. And there that heavier isotope will be dissociated little slower or that little it is little difficult. Whether it is slow or difficult, easy or difficult. But one thing I want to say, that thing is not going to affect, right? Not going to affect this time the rate of the reaction. Here the R1 and R3 will be same. Rate will be same. Because the Cl-Cl bond dissociation is not involved in the RDS, no? CH or CD bond dissociation involved in the RDS. What phenomena, what things are involved in the RDS? Only those things will be affecting here the rate of the reaction. And that's why here we find this difference, here we don't find the difference. And one more thing I want to tell you here. When we compare, you may have some different logic also. He said, at least their HNCl37 bond kind of thing forms now. They are the two types of effect, right? One is the primary isotopic effect. Other one is the secondary isotopic effect. So whatever we are comparing only primary isotopic effect. We don't compare secondary isotopic effect. That is negligible. What is the primary isotopic effect? Primary isotopic effect when there that isotopic bond strength is affecting the rate of the reaction. That is the primary isotopic effect. If there is hyperconjugation, inductive effect, or any other electronic effect of isotope is affecting the rate of the reaction, that is a secondary one. Okay, so that thing also you keep in your mind. Okay, fine. We take here now one more thing. Anyway, we are discussing here that I was discussing the kinetics, we have discussed the RTS, we have seen this one, that how that thing is affecting the rate of the reaction. But in this context, one more thing is very important what we need to know. You know that the reactivity of the CH you have learned, but the reactivity of halogen is also important. Reactivity of halogen is also important. How that is important? Because what we observe that F2 is very, very reactive. After that, it is the Cl2, then there the Br2, again there the I2 is deadly slow. This is the F2 very fast, then there the Cl2, then there the Br2, then there the I2. I2 is very slow, F2 is very fast. What very fast? You know, it's vigorous reaction, it's explosive reaction. You know what do you mean by explosive? Explosive means a small amount of the reactants produce large amount of energy. So the best example I'm telling you here, you see that what happens with this one. When there the CH4 reacts with F2, you know what it gives? It gives carbon N4HF. Yes, it gives like this. It gives carbon N4HF. It's not simply there that not happening, but actually it is cleaving, it is breaking all the bonds completely oxidized. It's vigorous, it's explosive, and that's why we don't perform fluorination reaction of alkenes. No fluorination reaction of the alkene, right? Sir, what about the I2? Sir, I2 is deadly slow. I2 is deadly slow. What is wrong with this one? You see this one. I will discuss, otherwise you see this point that why. You can ask that why it is there. There are the 2 points what we discussed. You know, we have discussed here the 2 points. First thing is, there the CH3 and there the H plus F that forms here the CH3 free radical and there the HF. And CH3 free radical that reacts with F2 and that gives here the CH3 and there the F and there the F free radical. This one is the CP1. You think of the CP1. This one is highly exothermic one. Highly exothermic means, you know, large amount of energy is released. So what is the source of that energy? Yes, source of energy. You see this one that everything is there in this reaction only. 2 things are happening here. The CH bond dissociation takes place and HF bond formation takes place. It requires energy, it releases energy. It involves bond formation, it involves bond dissociation. Bond dissociation requires energy, bond formation releases energy. Whether this state is exothermic or endothermic, it all depends on the fact that in this bond formation, the energy released is more than the energy required or equal or less. If it is more, then overall energy is released. If it is less, overall energy is required. That becomes endothermic. If this is more than the energy required, it is exothermic. And it is highly exothermic. Why highly exothermic? Because you tell me the bond comparison. There the HF, HCl, HBr and there HI, which is the strongest one? Bond strength. HF is the strongest bond, then there the HCl, then the HBr and HI. HF is the very, very strong. And you know it very well. That if that bond is strong, it means that has much lower energy and that has released large amount of energy. In the formation of the stable bond, there the large amount of energy is released, and fortunately, you will find that here in one HF formation, that much amount of energy is released, which is enough to break here 2, 3 CH bonds, not one. That can compensate the amount of energy required for the 2 to 3. Those many CH will be dissociated in one shot. That much amount of energy is released. First step is also exothermic, and that is the mainly exothermic. Second step is also highly exothermic, large amount of energy is released, because again, if you compare which bond is stronger, CF, CCl, CBr, and there the CI. CF is the strongest bond. Then there the CCl, CBr. Right? Large amount of energy is released. Okay. And that makes this one exothermic, vigorous one, not controlled reaction, right? We take here now, as I said that we take here now the iodination. In iodination, what happens? Iodination, in iodination, there CH3 and there the H plus I free radical. This will be taking here, and this will give here the CH3 radical, there the HI. There the CH3 free radical, that will take with the I2. This will take here the iodine, will form here the CH3I and there the I free radical. First thing is this one, this is the endothermic state, because HI is very weak bond, very less amount of energy is required, and that is lesser than the amount of energy required in the CH bond dissociation, endothermic. A second thing, this state is also endothermic. C and I bond formation, CI bond is also weaker bond, so there also it has no much tendency. Now in this case, this state, this reverse state is more feasible, spontaneous, energetically beneficial, favorable, and so this I free radical what forms, that will combine in I2 forms. Formation of I2 is energetically more beneficial than the formation of the CI. Overall, you write here, there the CH4 plus I2, and that gives here the CH3I plus HN. There is other way also to view this one. You know, other way is also there. What is the other way to understand? HI, what do you think about HI? HI is very strong reducing agent. A strong reducing agent. So what? Strong reducing agent that will reduce, that will act over this one and will reverse this one. Will reverse this process. Very strongly it reverses. And this reaction is not successful. Then, yes, in chemistry you can manipulate everything. You can manipulate this also. This manipulation is possible. How we manipulate this process, that I am telling you. Let's analyze that. What is responsible for the failure of this iodide formation? HI. HI is responsible. HI is the reducing agent. So when we are very determined to take here this iodide formation forward, this reaction is performed. Iodination is performed in the presence of some oxidizing agents like HNO3, HiO3, HgCl2. Yes, these are HgCl2, HNO3, HiO3, HgCl2. These oxidizing agents are taken. If oxidizing agent is there, immediately that oxidizing agent will work over this reducing agent, will nullify its impact, and this reducing agent will not be in condition to attack over this CH3I and cannot reverse this process. This way, this reaction can be manipulated and can be pushed forward. I hope you got it. All right. Here. Now let's take here the chlorination and bromination. One thing is very clear that iodination is deadly slow because of its reversible nature, because of its reducing nature. But one thing we have learned that here this can be performed well if some of the oxidizing agents are used. Right? Second thing, here now we take chlorination and bromination. Chlorination is certainly very fast. Not like fluorination, but chlorination is first. Now the point is here of the Regio chemistry, selectivity, right? I discuss here one thing that no doubt we learned it very well. Tertiary hydrogen is more reactive than the secondary. Secondary is more reactive than the primary. Yes, that is true. That is true for the chlorination also, bromination also. But here the reactivity is a little different. So here we are discussing this point, that is the reactivity and selectivity. Reactivity and selectivity. Selectivity. There is one general statement: higher the reactivity, lesser the selectivity, and lesser the reactivity, higher the selectivity. This is the Regio selectivity in general, because we say out of various possible structural isomers, if one of the structural isomers is the major one, prominent one, then the reaction is called Regio selective. Then the reaction is called Regio selective. For example, I'm telling you here, first I take here some data, and then you will understand better. Okay. So I discuss here the reactivity of CH, the quantitative form, reactivity of CH. This one is primary, this one secondary, this one tertiary. But fortunately, unfortunately, there you get here the different data. For there the chlorine and for the bromine. When the chlorine, we have the quantitative data here. It is believed that primary CH, if that is reactive towards chlorine 1 unit, then the 2 degrees is 3.8 times more reactive than this one. That is true. 2 degrees more reactive than this one. And how much? That we get the idea. 3.8 times more than the primary. A tertiary is much more reactive, and for the chlorine, it is the 5 unit. Yes, what you know, what we were knowing, that all is there. There the 5. After when the class will be over, right now, that time I can advise you some of the books, right? Let's finish this part. After that, I will certainly advise some of the books. So 1, 3.8, and there the 5. Okay, 5 times it is more reactive. When we think here the bromine, and if you consider here the primary hydrogen, that is 1 unit, 2 degrees, certainly more reactive. But this one is 82 times more than this primary. And tertiary is 1600 times more reactive than this primary. Here also the order is tertiary, secondary, primary. There also order is tertiary, secondary, primary. But this difference is less in the case of chlorine, and this difference is more in the case of bromine. Why? It shows selectivity. As the chlorine is more reactive, that's why this kind of selectivity difference is less in between primary, secondary, and tertiary. But as the bromine is less reactive, so this one is more selective, and that's why we find the tendency towards reactivity for the secondary is very significantly higher in comparison to this primary, and tertiary is dramatically higher. And you can estimate this impact also, because with the help of this quantitative figure, you can find here the relative yield. Relative yield you can find. Relative yield is in comparison to this one. What is the relative yield? Relative yield Ry is equal to there the reactivity of those hydrogens into there the number of hydrogens. Number of hydrogens. Honestly speaking, you know, I said this one kinetic factor. I said this one probability factor. This is the product of kinetic and probability factor. One is kinetic factor, other one is the probability factor. What do you mean by probability factor, sir? You see this one. If I say that here we have one molecule like CH3 and there the CH2CH3 that reacts with Cl2 in the presence of H nu, then the chlorine atom what forms in this process, what is the probability of its collision with the primary hydrogens? Because they are the two products. There 3, 6, and so CH3, CH2, CH2Cl. How many products will form? Two products will form. We have 3 hydrogens here, 3 hydrogens here, 6 primary hydrogens, and if that chlorine atom collides with any of the 6 same product, so the probability factor is 6. Means the number of hydrogens with which it collides, that is the number of hydrogens, that is the probability factor, probability of its formation. When that will collide with those hydrogens, then only their reaction will be taking place, no? Then only the product will be happening there, no? So what is the probability of its formation? 6. What is the number of hydrogens responsible for this one? 6. So you can find here the reactivity, there the relative yield. What is the relative yield? Primary product, so what about the reactivity of the primary? 1 unit. So reactivity is equal to 1. And what is the relative yield of this one? There, sorry. Number of hydrogens responsible for this product only? 3 and 3, 6, because I told you, I explained you. Any of the 6 collision with any of the 6 will give the same product. So the number of hydrogens responsible for this kind of product is 6, and 1 into 6 is equal to 6. That is the relative yield of this. What is the other product possible? Other product is this one. There is CH3, CHCl, and there the CH3. How many hydrogens are responsible for this one? How many hydrogens are responsible for this one? This is secondary one, and there are the 2 hydrogens, and if that chlorine atom collides with any of these 2, you will get the same product. There are the 2 hydrogens, and both will be giving the same product. So we say the probability of its formation is 2. Probability factor. And 2 hydrogens are responsible for this product. So the number of hydrogens will be 2 for this one. In which hydrogen is this secondary one? And what's the reactivity value? Reactivity value is there 3.8. So the relative yield is equal to there the 3.8 into 2 is equal to 7.6. The relative yield of this one, this product is 7.6 and that product is 6, and then you can understand that what's the difference, right? Almost similar. You can find there the percentage also. 6 by 13.66 plus 7.6, 13.6 is the total value. And 6 upon 13.6 into 100 is this percentage. And there the 7.6 divided by there the 13.6 into 100 is the percentage of this one. You can find relative yield also and there the percentage also. At the same time, if you take here the bromination, it is the Br2 and there the H nu. Two products form CH3CH2 and there the CH2Br. What is the relative yield of this? They are the same thing. 6 hydrogens are responsible. Reactivity is 1 into there the 6 is equal to 6. But when we write here the other one CH3CH and here Br CH3. What is the relative yield of this? Relative yield is equal to there that 82 into 164. Now you see this. What is the percentage of this one? What is the percentage of that? In this case, in the case of coordination, this secondary and primary both are almost similar in terms of yield. But in this case, both are significantly different. This one is 164, this one is 6. This one is negligible. This is called selectivity. Bromination is very much selective for this secondary place, and that's why this is the higher yield. That's why we say higher the reactivity, lesser the selectivity. Lesser the reactivity, higher the selectivity. 164 secondary is dominating one. I hope it is clear, right? Here we discuss some other aspect now. We discuss here CH3, CH2, 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 CH3. It's a matter of Regio selectivity. And there is a Cl2 and H2. How many products? Sir, primary and secondary. No. It's not limited to primary and secondary. Here, when we write this one, you go for this one. What's the product here? 1, 2, 3, 4, 5. 1 chloropentane. CH3, CH2, 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 CH. This is one. How many hydrogens are responsible for this one? 6. Because if the reaction takes place here, then also same. Yes. So both are same. Both are same. Both are same. Why same? Because reaction here and there give the same product. We say all these 6 hydrogens are equivalent because we are getting the same product. All these 6 primary hydrogens are equivalent because all these 6 primary hydrogens are giving the same product. Okay. Come to this one. When the reaction takes place here, we get here CH3, CH2, CH2, CHCl, and there the CH3. In this case, this one is secondary. Can we say that all these 6 secondary hydrogens will give the same one? No, will not give the same one, right? Will not give the same one. Okay. 1 minute. Will not give the same one. But these will give the same one. If the reaction takes place here or there, we will get the same. So what we say? All these 4 secondary hydrogens are equivalent. Why equivalent? Because chlorination of all the 4 will be giving the same product. That's why equivalent. What about this one? Yes, this one is different. Sir, that is also secondary. Yes, all secondary may not be same. There the CH, Cl, CH2, CH3. This one is secondary. This one is secondary, right? This one is secondary. And how many hydrogens are responsible for this one? Only 2 hydrogens are responsible. Only 2 hydrogens are responsible. So these secondary hydrogens are different from those secondary hydrogens. Different. Now the question is there, how many different kind of hydrogens we have? There 3 different hydrogens we have. How many different monochlorinated products we have? 3 different monochlorinated products. This one, this one, this one. Okay. 3 different monochlorinated products. All the primary hydrogens may or may not be same. All the secondary hydrogens may or may not be same. All tertiary hydrogens may or may not be same. Then which are same? All those primary hydrogens which will be giving the same chlorinated product will be equivalent, will be giving the same product. All those secondary hydrogens which are giving the same product, those are equivalent hydrogens. And all tertiary, right, which will give the same, those are equivalent, right? Sometimes very simple question is asked. Based on this only, very simple question is asked. There, there is an organic compound A. Its molecular formula is say 6H14. On monochlorination gives only 2 products. Only 2 products. What could be the structure of A? What could be the structure of A? A is 6H14. Molecular formula is given. Molecular formula is given. Okay. On monochlorination gives here only 2 products. So now this information is helping us to interpret structure. Interpret structure. You see this. Here, this one is CH3, CH2, 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 CH3. This is one of the possible structures. How many monochlorinated products will be there? How many? If this is the 6H14, then this will be giving 1, this one same, this one same, this one same. 3 products. If we write here CH3, CH, let's explore all the possible ones. CH2, 1, 2, 3, 4, 5, and 6. How many different products it will be? Here, this one, you see, this one and this one, both are different. Different. primary only but different. Because if the reaction takes place here, this is a 1 chloro 2 methyl pentane. If the reaction takes place here, this one is 1 chloro 2 3 4 methyl pentane. Both are giving the different products. But if you take here these two, yes, same. Because if the reaction takes place 1 chloro 2 methyl pentane, there also 1 chloro 2 methyl pentane. So these two are equivalent. So one product you will be getting here and there. Here, there, together, all these six will be giving one product. This will be giving one product. This one is the tertiary. This will also be giving the one product only because this secondary and that secondary will be different. Because if the reaction takes place here, you will say 3 chloro 2 methyl pentane. But if the reaction takes place here, you will say there the 2 chloro 4 methyl pentane. Both are different. And this one is also different. So total how many? In this case, 1, 2, 3, 4. This will be giving the 5 different monochlorinated products. 5 different monochlorinated products. This is also not A. We take here CH3, CH2, and there the CH3, CH2, CH3. How many? In this case, these two are same. In this case, these two are same. This one is different. This one is different. Correct? No? Here, these two are same. These two are also same. This one different. This one different. Total, how many? 1, 2, 3, 4. This will be giving here the 4. This is structure. Okay. We take here the other structure also. We take other structure CH3C, CH3, and there the CH3, CH2CH3. How many for this one? Here, this one, and this one, all are equivalent. Can we say that these hydrogens and those hydrogens are equivalent? No. Because if their reaction takes place, this will be 1 chloro 2 dimethyl butane. If their reaction takes place, this is 1 chloro 3 and 3 dimethyl butane. Both are different. So these will be giving one product, and this will be giving here one product, and this will be giving here one product. Total how many? There are also 3. What is this A? Next one. There is CH3, 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 and there the CH3. I could have written in the beginning also, but I had to discuss how to answer this question. So there, all these are equivalent. All these primary hydrogens are equal, one product. And all these two tertiary hydrogens are equivalent. Again, one product. Total how many? 2 products. This one is, so this one is A. This one is A. I hope you got it, right? Yes. We will discuss here now the other aspect, right? That is stereochemistry of this one. We'll take here one of the very important concept, that is the stereochemistry. The stereochemistry of this reaction. What is the stereochemistry? Yes. Give me 1 minute, okay? Just 1 minute, please. In this stereochemistry, first thing what we have to understand, take here the simplistic example. CH3, CH2, CH2CS. Right? There the coordination takes place. Cl2 and H nu. You know that this reaction proceeds through a radical intermediate. Radical intermediate. And what is the radical intermediate? What is the hybridization of this one? This one is just 3. What is the geometry of this one? Trigonal planar. Trigonal planar. So in this reaction, what intermediate forms? Intermediate forms here. That is CH3, CH2, CH. I am talking about the reaction here. Primary, it's okay, you know. I am talking about the reaction at the secondary place. Okay. This is the free radical. And I said that this free radical is sp2 hybridized in trigonal planar. So what is this? This one is you write here in the proper way. Huh? You write here the proper way. We write here CH2CH3. This one is hydrogen, and this one is CH3. Here the CH2CH3, this one is back of this one is coming towards you, and there is one of the unhybridized orbital which keeps one of the electrons. Now there the chlorine reacts with this one, there the Cl2. This may combine from this side also, this side also. This is the sp2 hybridized. Trigonal planar. Both faces are equally open. So if this happens, different product, and if that happens, different. How? So let's write. If that happens, then what? Then you write here C2H5, exactly the Cl comes here. Then these groups will be moving away, and this one H, this one is CH3. Okay. And if the attack takes place from this side, there the C2H5, Cl is here, there hydrogen, there CS3. Understand this? There, this is very simple to understand. You can take here some of the pain and then the pencils, and you can explain this one. This one is basically there. All these three are in the same plane, like this one. This one is CH2, CH3, this one CH3, this one hydrogen. And if the attack takes place from there, all turn like this. That's a simple thing. Simple thing. It is like tetrahedral now. Otherwise, same plane. If attack takes place from there, simple tetrahedral now. Turn around that side. Exactly. That way, turn it over. If that way, then this way. So this is color, that is color. These two appear as mirror images. And so what is it? You say this one, what's the configuration of this one? This one, this one, two, this one, three, one, two, three. Ah. This one is one, this one, two, this one, three. This one is what are these two? These two are 50% this one, 50% that one. This is a kind of there the reaction when equal attack on the two faces take place, and we get here the equal or the equipolar mixture of these two enantiomers. What we say this one? We say racemic mix. Stereochemically, we are getting here the two different products, and this process is called racemase. So if the question is there, how many product it gives? Total number of monoprotonated products in this case. Number of total monoprotonated products. Total monoprotonated products, it means including stereoisomers, including stereoisomers. On this place, one product. Here together one. Here they are same. But on this place, how many you are getting? Two products. What are those two? R2-chlorobutane and S2-chlorobutane. Total products we are getting here, three. One here, two there. Right? We say this one R2-chlorobutane and S2-chlorobutane. Like this, two products on this place. Total products, three, including stereoisomers. Right? Now, I am discussing here one of the questions which has been, right, the best question of IIT JEE history. Best question of IIT JEE history. You know, because the very first this question was there asked in 1999, and then next 2003, next 2007, next 2011, next 2012 JEE means that time. Again there the 2017, 2018 means here this concept is very important in the extension of this concept was the basis of that question. Here the question is CH3, CH3, CH2, CH3. Here that is treated with Cl2H nu. Monochlorination takes place. Total number of products P. Further fractional distillation is performed. Fractional distillation performed. There the Q, number of fractions. I know many people know the answer. But when I discuss, when I start asking, they are confused, giving the wrong answer. Otherwise, no correct answer. But when I start arguing, then finally come to conclusion, giving the wrong answer. Again, when I explain, then again giving the correct answer. So it is happening in most of the cases. Here, let's discuss this question. First reaction takes place here. Yes. This one is CH3. There the CH3, CH2, and there the CH2Cl. 1-chloro, 3-methyl-butane. Yes, different product. When there the free radical forms, attack will be taking place here and there. Will that give the different product? No, will not be giving the different product. Same product. This is not the chiral center. This is not optically active. Same. Okay, let's take here the reaction here. This is called prochiral center. What we say this one? Prochiral center. Why this is prochiral center? Because the monocoordination reaction of this place makes this one chiral. That's why this is called prochiral center. And here you write CH3, CH3, CH, and there the Cl, CH3. When there the free radical forms, attack sp2 have this trigonal planet, attack will be taking place from the two sides. Will you getting here the two different products? Yes. You are getting here the two different products, plus and minus R and S. Racemic mixture you are getting. This is the prochiral center. Racemization takes place here. Two different products there. I can explain you this one in any way. You learn this one. This one is you make this one IPR, isopropyl. And so when you take here this one, you write this. This one is IPR, isopropyl. Sorry. This one is H. This one CH3. There, the one electron, unpaired electron. Coordination takes place from this side and that side. And we will be giving the different products. Yes, IPR. There is Cl, H, and Cs. This way, IPR, here is the Cl. There the H, Cs. What are these two mirror images, plus and minus? Yes, there on this place racemization takes. We get here the two different products. Now, come to this place. What happens here? Reaction takes place. And we get here the CH3, CH3. There Cl, CH2, CH3. There also attack may be taking place from here and there. Are you getting here the two products or one product? One product. This is not the chiral one. Methyl and methyl similar groups. One product we are getting. This is not the prochiral center. One product only we are getting. Okay, fine. Right. There is no chiral center in this case. In this case, there is one chiral center, and you are getting here racemization takes place. The other two. Now, a reaction will be taking place here or there, and already you know that these two are giving same products. Let's take here CH2 free radical forms. Now there is again chance that attack will be taking place from here and there. Will you get here the two different products? This is not the chiral center now. So if the attack will be taking place from here and from there, it will be giving the same product. And so this one is Cl, CH2, CH, CH3, CH2, CH. Although this is the chiral, but this is in this case that carbon is not the chiral where the reaction takes place. Reaction takes place here, that becomes chiral center. So can you say that here we will have the different configuration? Oh, reaction is taking place here from the two different sides. There is chance of the different configuration, but how there the configuration will be different. It's difficult. So how many products for this one? Can you say here there is one chiral center? That's why I said chiral center. So the two. This blind old rule is not correct. If you say here, I will trap you in another question. And Jay has already prepared that kind of question to trap those persons who are taking this kind of blindfold answer. So altogether, how many? Here one. Here how many? Two. Here how many? One. And here how many? 2, 1, 3, 1, 4. And here 1 or 2. The concept what you know so far, as per that only one. As per that only one. But you all know, I know this one. You all know answer is 6. Answer is 6 that you know. Because this is the previous writing question. Everyone knows the answer. Right? But you should know the right region of the answer. Right? That is the beauty of the idea. I just explained this one in just 1 minute now. Okay? You see. When you write here the CH3, CH3, what is the beauty of this question? You will see in this case CH2, CH3. This is the truly advanced. This one is the ethyl, this one methyl, and this one is one of the center where the reaction is not taking place. Reaction will be taking place. I write here this as one of the stereochemical center. CH2, CH3. I write here the hydrogen. And this one is CH3, this one is CH3. We have discussed that if the reaction takes place here and there, we get the same product. Yes, same product. 1,chloro-2-methyl-butene. There also 1,chloro-2-methyl-butene. But honestly speaking, a reaction on this place, and that place give the different products. Main concept is this one, right? Reaction here and there gave different products, not structurally, stereochemically. Structurally, these two are equivalent, but stereochemically, these two are not equivalent. You see this one? That if the reaction takes place here, you get CH2CH3. Their hydrogen as this one, so this one is CH2Cl. This one is CH3. If the reaction takes place here, there is CH2CH3. Here hydrogen. There CH3. And this one is CH2Cl. What do you say? Their reaction takes place this one. Their reaction takes place that one. Are these two same or different? Different. These two are different. This is of the highest priority. This one is second. This one third. This one 1. This one 2. This one 3. 1, 2, 3. R. Configuration is R here. This one is 1. This one 2. This one 3. 1, 2, 3. This one is S. Its configuration. This one is R. This one is. Here that concept is not working, that here there is a chiral center, so you take here the two. No, wrong. This has a different concept. This one is a reaction at enantiotrophic phase. Enantiotrophic phase. This phase is called enantiotrophic because when the reaction takes place on the enantiotrophic phase, the chirality appears on some other place. Reaction on the prochiral center is different, and reaction on enantiotrophic phase is different. There also racemization takes place. 50% attack will be here, 50% attack will be there, but attack on this place makes this one is chiral center. We get this one 50%. Attack on this place, we get this one 50%. We get here the 2 products, total 6 products. Okay. Here, one thing I want to tell you that we have very good questions, but today, unfortunately, we have shortage of time. Some other day, we'll discuss the ultimate questions. This is the best part of JEE Advanced level of questions. If you'll see the previous year questions, you'll find number of questions from this part and very conceptual, mind-blowing questions, right in advance. We will discuss in some other class, some other day. Here, few things I want to tell you. That the basic approach of teaching advanced is only one thing that you ask, will question yourself. Why? Why not this? Why not that? Advanced is not really advanced. Advanced means really more basics. When we start entering into deeper and deeper, more basics in basics, that becomes advanced. Going deeper is advanced, not going higher is advanced, right? Many people can create one of the very exceptional what reactions are not known, what reagents are not known. Array, that is not advanced. Reagent is not known, so what one person can do? Everything is known. That time, asking one of the question based on the process of its formation, process of stereochemistry, attack, the solvent, temperature, many other aspects, components. That makes this one advanced. First thing. Second thing is this one, as some of the gentlemen asked me, there are some of the good book. Honestly speaking, if you take any, there are the two kind of approach. One, immediate solution, Indian books. Permanent solution. They are the foreign authors, very good level of books. Standard textbooks. A standard textbook, it means IL best book. It's difficult to read this one, very boring. Other boring book is the Jerry March, but both are exceptionally good. And you know, when you read something from that one, no one can challenge you. The best part is this one, no one can challenge your fact because you are using the most accepted, widely accepted reference books. If you use their Jagdamba Singh, immediate solution, Jagdamba Singh, OP Tendon, immediate solution, Jagdamba Singh is the best solution. R.K. Gupta, R.K. Amit. Immediate solution, it means these books you can read. But really, if you want to put your own idea, very standard idea, then you have to follow this book, right? Organic chemistry, it's otherwise if you have any other book like Lauder or any book you take, right? If you read everything properly, that is creating miracle. You can take here Wade Junior also, Lauder, or this. Uh, Honestly speaking, no one is reading that one. Morrison White is also very good, but people find it difficult to read. Don't have the patience to read. Hmm. All these books are good. As I told you, for immediate solution, the first thing you can use. Okay, one thing. Second thing, if you want to see there the physical chemistry, if you want really to make the concept again, I'm telling you, not the foreign author books. I will say KL Kapoor unit. It's again, you find your own part what things are concerned. You have to find your concerned things, not everything, and don't go everything. Otherwise, to understand the real thing, there is a very simple book, right? No? Very simple. That book also you can modify. That is a general chemistry, but the way it has been written, you will understand that will unblock the way of thinking. That is the real way. So you understand that kind of book can develop you. Otherwise, physical chemistry, you can take the Pradeep. Oh, I mean to say that Balaji publication, right, Prabhat Kumar, or the other OP Tendon. Immediate solution means these books are really enough. But permanent solution, KL Kapoor, Modife, that kind of book really make your concepts very clear. You get the fun concept, logics behind everything. Then you will be the master. You will get confidence. Yes, I know the thing. I know all the aspects, and that makes you perfect, right? I wish you all the best. I will keep on meeting right now. And if possible, I will take another session. As I told you, some of the brainstorming questions are there in this part. We will discuss later. Thank you. Good night.